Log on, tune in, find out. Another good idea from Cambridge.
Next speaker is Alejandro Chavez Dominguez, who will speak about duality for Lipschitz p-summing operators.
Okay, so is this working?
Yeah.
Is the microphone in?
Okay.
So
No?
I need switching on. Did you
So-
turn it on?
How is it?
There's on the top.
Okay. So it should be working now. At the risk of sounding cliche, let me start by thanking the organizers for inviting me here. And let me also thank you all for being here, being late on the last talk of the day and without a break. So let me start with a little piece of notation. X, Y, and Z will always be metric spaces, whereas E, F, and G will always be Banach spaces. I mentioned this now, so I don't have to be repeating this over and over again. So I will be talking about duality for Lipschitz p-summing operators, whatever that means. So since this is a workshop on embeddings, let me start the story talking about embeddings. So there is this famous theorem of Bourgain. Which one, you may ask, being that there are so many famous theorems of Bourgain. So I refer to the one about embedding finite metric spaces into Hilbert space. So any metric space on n points can be embedded into Hilbert space with distortion at most a constant times log n. So what does that mean? If I have my finite metric space X and a Hilbert space, I can find a function f so that the Lipschitz constant of f times Lipschitz constant of the inverse is bounded by this universal constant times the logarithm of the number of points. So let me look at this in terms of this diagram. I can say that there is this inverse on this side. But this is not defined on all of H, so that's why I'm not using a continuous line, right? So, okay, this is the situation described in Bourgain's theorem, at least in the usual way. But if we look carefully at the construction, maybe not even so carefully, we can see that there is more to it. There have been several observations regarding how there is more in here, so I'm going to be speaking about a particular thing. This Hilbert space is in fact L2 of a probability space and this bound on the distortion is still true if we go through L infinity first, right? So okay, this is starting to look familiar. So if I look at the identity on X, and I look at this diagram, this is actually very familiar for the people in Banach space theory. This is very reminiscent of the diagram that describes p-summing operators, in this case, two summing operators. So let me say what that means, and you will see why this is very similar. So definition slash theorem due to pitch a linear operator between Banach spaces is p-summing if one of the following conditions is satisfied. Equivalent So number one, the existence of a diagram like this P is going to be between 1 and infinity. With A and B linear bounded operators. And here again, B is only defined on a subspace. Or number two, there exists a constant greater than 0, such that whenever we take vectors in the domain, we have a certain inequality. So here E star is the dual of E. And this inequality, what it's saying is we're sending weakly p-summable sequences into strongly p-summable sequences. Okay, so this is the definition slash theorem, but this is a linear situation. This is talking about linear operators between Banach spaces. And the other diagram I have up there, however similar, is not in the same category. That is between metric spaces, and I have Lipschitz functions. So how do we relate one and the other? Well, that has been done. So another definition theorem. This one due to Farmer and Johnson. So now we're going to have a Lipschitz map. I'm going to abuse the notation and call it T again. But this one goes between metric spaces, not Banach spaces. It's going to be called Lipschitz p-summing if it satisfies one of the equivalent conditions. So number one is going to be the existence of a diagram just like that. And let me be very clear here. A and B should be Lipschitz functions. And something else I have not mentioned is these arrows I have between L infinity and LP are just the natural inclusion, right? So on the left side, A and B are linear operators between Banach spaces. On the right side, they are just Lipschitz mappings between metric spaces. And the second condition that is going to be equivalent to this is again the existence of a constant such that for any, now instead of taking vectors in the domain, we're going to have points in the domain. They are not vectors anymore. And we have a similar looking inequality. Instead of norms, now we have distances. And it has to be bounded by something very similar. Okay, so we're sort of playing a game, trying to go from a linear situation into a non-linear one. So there are some parts where we know what to do. If we have a norm, we replace it by a distance because that's what we have. But what do we do here? What do we do about the dual? A Banach space has a nice dual. It's another Banach space. But what about a metric space? There is no such thing as another metric space that is its dual. So what we use is called the Lipschitz dual. So this Lipschitz dual is going to be the set of all real valued functions defined on X and that are Lipschitz. And I made a mistake here. I meant the unit ball of the dual. And this space is going to be considered with the Lipschitz norm. There is a little technicality that this is not actually a norm but a semi-norm. In order to fix that, we add an extra condition that f of 0 is 0, where this 0 on the left is just a fixed point in our metric space X that we're going to call 0, and it's sort of the origin. And that's not important at all. So, okay, this looks very similar to a linear situation. We even have this theorem of Farmer and Johnson saying that the equivalence still holds, but so far it could be just a game. It could have nothing to do with the other situation. So another important piece of the puzzle is another theorem of Farmer and Johnson saying that if U is a bounded linear operator, then it is p-summing if and only if it is Lipschitz p-summing. And even more, if we denote the infimum of such constants by sub p, and here by the same thing with the superscript of L, then they are going to be equal whenever the operator is linear between Banach spaces. So this is actually a generalization of the linear situation. We have a more general concept between metric spaces, and it happens that for linear operators, both notions coincide, even up to the constant. Okay, so this is sort of the background, the setting. So let me go on and talk about this duality thing. So where does this duality come from? So if we fix, say, a metric space X, E a Banach space, and we consider two different mappings from X to E, it's really easy to see from, say, condition number 2 that this Lipschitz p-summing constant is going to behave well with respect to addition, point-wise addition. So that means that modulo taking care of these technicalities of sending 0 to 0, the space of Lipschitz p-summing map from X to E is a normed space. We will denote it with a capital phi. So being a normed space, it has a dual. So what is this dual? So first of all, why should we care about such an object? Well, p-summing operators have been greatly useful in the theory of Banach spaces, even in some places where one wouldn't expect to find them. And they have been used all over the place for many years, and well, they are a great tool. So if we could do something like that for the non-linear theory, that would be great. And well, why care about duals? Well, in Banach spaces, whenever we have a space, we like to have non-trivial expressions for the dual because that helps with calculations. So here's the situation. We're trying to identify the dual space of the space of Lipschitz p-summing maps from a metric space to a Banach space. So how do we start? Well, since this all started from the linear theory, why not look for inspiration in the linear theory? So what do we know about, say, the corresponding linear situation? If we look at the space of p-summing operators between two Banach spaces, what is the dual? Is that known? Well, of course it's known.
There's one more ball.
Yeah. So maybe I should keep this one. And get rid of Yeah, I don't want to use the side ones because they're rather difficult to see from some places. Okay, so what about the linear situation? What is the dual of the space of P summing maps between two Banach spaces? Well, that's known. That's either nuclear or integral operators from F to E. So whatever that means, it's a space of operators that go back, go the other way, go from F to E. So in our nonlinear setting, that's not going to be good because there is no good way to define functions going back from the Banach space into the finite metric space. They're not even going to be continuous unless they're constant. So this search for inspiration in the linear theory doesn't seem to look so successful. There is, however, another piece of information in the linear theory that ends up being useful. And that's the Chebet-Safar tensor norms. So the idea is there is a way to give a norm to the tensor product of two Banach spaces in such a way that what we get is precisely P summing operators. So before I tell a lie, let me make sure I do it properly. So this dp, whatever it is a norm on the tensor product of these two Banach spaces. So this is related to P summing operators in this way. And how on earth could we possibly relate this to our nonlinear situation? Well, we would need some sort of nonlinear tensor product, and that's precisely what we're after. So, as a warm-up, let me consider a specific situation. What if we consider P equals infinity and the simplest possible Banach space, the real line? What is this space of P summing operators? Well, P is Lipschitz p-summing. Well, it's going to be a space of real valued functions defined on X. And what is this Lipschitz infinity summing norm? Well, if we go back to the definition, we can see that it's just going to be the Lipschitz norm. It's particularly easy to see here. If p equals infinity, this factorization says nothing. It's just the Lipschitz norm. So, in particular, we're looking at trying to identify the dual of the space of Lipschitz functions defined on a metric space. And, well, that's kind of a bad idea because these spaces are rather large and ugly and we don't know much about them. However, we do know that this space is a dual space. This f of x is called the Arens yield space of x. So if we go with the original question of Farmer and Johnson, trying to find the dual of the space of Lipschitz p-summing operators, we run into trouble. Even the simplest possible situation of all is too much. So if we flip the coin, we're in better shape. Instead of trying to find the dual, we can try to find a pre-dual. And that's going to be much more manageable. And in fact, we have part of the work already done in this Arens-Yield space. So let me tell you what this Arens-Yield space is. There are several different ways of looking at it. So this is the original definition of Arens and yields. A molecule is a finitely supported function, say m, from our metric space into the real line, such that the sum of all the values is 0. So since no matter what x is, since we're only considering finitely supported functions, this sum makes sense. So what are the simplest possible molecules of them all? Well, besides the 0 function. It would be taking at one point one value, say 1, at some other point -1, 0 everywhere else, and this would be a molecule. So if this point is x and this point is x prime, this function is going to be denoted m of x prime. So it's the indicator function of the singleton x minus the indicator function of the singleton x prime. So this little special functions will be called atoms. And why are those called molecules and these ones atoms? Because every molecule can be made up out of atoms. For every molecule, we can write the molecule as a linear combination of atoms. There is, of course, no unique way of doing this. There are many ways of doing so. And this is going to be used to define the Arens-Illes norm of the molecule. It's going to be the infimum of these expressions. So I take my molecule, which is this function that adds up to 0. I express it as a linear combination of these atoms. And I look at this sort of L1, little L1 norm of the coefficients weighted with the distances. And this is the Arens-Illes norm. So what's so special about this space? If I take molecules with this norm, this is what I previously called F, and I'm mixing notations. That's because this space is also called the Lipschitz free space of X. So this space has the property that its dual is the space of Lipschitz functions on X. Okay, so this is sort of the baby case, right? P equals infinity, E equals the real line. So how do we go up to the Lipschitz p-summing operators? Well, I was talking previously about these tensor norms that are related to p-summing norms. And we have this here that is actually very reminiscent of a tensor norm, the projective tensor norm. So if I have a tensor and I write it as a sum of elementary tensors, this is called the projective tensor norm of the tensor. And well, this sort of provides the link. Oh, thank you. So this expression and this expression here, they are in correspondence under this same principle that we have used earlier of replacing norms with distances. So we kind of have all the ingredients. We can start building this nonlinear version of the Chebet-Safar tensor norms. So now we generalize this idea of Arens and Illes of molecules and we define an E-valued molecule. And what is it? Well, just what it has to be. An E-valued function, finitely supported again, such that the values add up to 0. Now the atoms are going to be slightly more complicated. It's just the same elementary functions we had, but now multiplied by a vector. And, well, we can look at the space of E-valued molecules defined on our metric space X. Now, how do we define the norm?
So here we mean m of x is v and m of x prime is minus v, right?
Yes. Yeah. That's right. Well, in order to know what to do, let's look at the linear definition of these Chebet-Safar norms. The Chebet-Safar norm of W is the infimum of this sort of mixed expression. If E in the ball of phi vj the p prime and p prime such that W is vj times vj. Okay, so that's a linear formula I didn't want to write before because it's a little bit ugly, but you can see how it relates with everything else. We have this strong p norm, this weak p prime norm, and it all sort of falls into place. So the nonlinear version, now we have M, an E-valued molecule, and well, the corresponding Chebet-Safar norm of M will be something slightly uglier. Supremum on the ball of x sharp sum of lambda j negative p prime where of course this infimum is taking over all possible ways of writing the molecule as a sum of atoms in this way, and all lambda j positive, and well, this lambda j is sort of an artifact of the proof. in order for this to look exactly like the other expression, I don't need the lambdas, right? However, if I don't have the lambdas, the resulting expression is not really a norm. So in order to make it work, we need these lambdas that are sort of hidden in the linear definition. In the linear definition, I can add these lambdas and nothing changes. Or in the nonlinear case, I need them. So this somewhat ugly looking expression gives rise to a norm, and the theorem, once we have the right formula, is for any metric space X and any Banach space E, the dual of the space of E-valued molecules on X with this norm is canonically identified with the space of Lipschitz p-prime summing operators from X into E star, and this duality is given just pointwise.
X is any metric space, not necessarily finite.
X is any metric space, not necessarily finite. As a corollary, whenever X is finite, we do have the reverse duality. The dual of the space of Lipschitz p-summing operators from X into E is going to be this Chevet-Safar space of the corresponding index taking values in the dual of E. But once we have this, this follows immediately just using the principle of local reflexivity. So it's just a standard technique. There's not much to say there. Okay, so we have this definition of Lipschitz p-summing operators. We had this question about the duality, and we found a way to identify this dual space. Now, what can we say about these spaces? Can we use them for anything? Do we know any of them? And well, I only know one little example. And it's the usual example. That is a tree.
X is a point.
Yeah. Well, if X is a point, there's
That's also true.
pretty much nothing. But what happens if X is a tree? In the graph theoretic sense. And say P is equal to 1. So the other extreme. Well, this expression, when P is equal to 1, simplifies. CS1 of a molecule is going to be the infimum of expressions like this, where of course M is So this is just an immediate generalization of the Arens-Ilse norm. And the difference is, the difference with the general case with P is this expression is easy to handle because we get rid of this ugly supremum over all the Lipschitz function on the unit ball of the dual. So we can actually handle this expression. And in the case of the tree, it's even simpler because we have to look at distances between points. So whenever we have
So
2
this
points.
is more general than for trees? When does this
Oh,
hold?
this holds
Just for people?
always for p equals 1. And it's quite simple, but in the case of trees, it's even simpler because whenever we look at the distance between 2 points, we have a unique path between them. So we can replace this representation of the molecule for one that uses only molecules corresponding to edges. And then use the triangle inequality and blah blah blah. So in the end, CS1 of a tree with values in any Banach space is just gonna be a little L1 sum of copies of E as many times as the tree has edges. But this is the only example that is known. Can we do anything else, let's say, theoretically with these spaces? Well, we can do something that I like, and that is we can replace a non-linear situation by a completely linear one. And that is another result. The following are equivalent. 1, T between x and y is Lipschitz P summing. This is a non-linear concept. And condition 2 is going to be completely linear. And this is for every Banach space E or only y sharp a certain linear operator induced by T has to be bounded. And what is this T sub E? Well, it is what it has to be. T sub E of a molecule living in this space has to be, well, corresponding molecule So we have a molecule and we're sort of trying to apply T, so there is only one place where we can apply it, and that is at the xj's. It's not completely obvious at first sight that this is actually well defined, but it is. One has to use the fact that the dual of the Arens-Ilse space is the space of Lipschitz functions. So, as I was saying, the flavor of this is we have a non-linear situation, and we're replacing it with a completely linear one. And that is all nice if one likes the linear situation, handling linear operators. However, we're paying the price of having to deal with rather complicated Banach spaces, these Cherev-Safar spaces. So let me finish by saying that this idea of molecules, I'm trying to apply it in some other situations, but I still don't have a handle on it yet. These molecules are rather difficult to work with. In particular, I can get an expression for the dual of the norm of factorization through a Hilbert space. So that's kind of nice, because in the particular case of the identity on a metric space, that would give us the Euclidean distortion. However, this formula is not manageable even for trees, at least so far. So let me finish 5 minutes early in case you have any questions. So thank you again.
Are there any questions? No? So thanks again. And we'll keep the water inside.